Okay, so we've covered the theory of trading systems. Now let's get down to the nuts and bolts. First, what are the crucial requirements for this trading application?
Right. We need to nail down the expected user base and how many different trading strategies it should handle, among other technical specs. It's all about defining the system's capabilities and limitations.
Okay, so we've established the requirements. Now let's delve into the services. How will these trading system components interact and scale?
Exactly. We need to determine if each service has its own database for optimal performance. What will the API design look like for each service and how will caching be implemented?
Okay, so we're diving into requirements elicitation. This is crucial, right? What specific user numbers and strategy limits should we be targeting?
Absolutely. We need precise figures for user volume and supported strategies. That defines the system's scope and potential. And it impacts everything from server capacity to data storage needs.
Great. With user needs defined, let's consider core entities like signal and indicator. How do these interact?
Signals rely on indicators for input, giving a yes/no response based on their values. Understanding this relationship is key for building the architecture.
So, indicators are basically formulas, right? Like Bollinger Band with calculations, or something more complex, like sentiment analysis from a text response?
Exactly. They take market data, news, order books, and calculate numeric values. Crucially, these values are then used by the system to make trading decisions.
And conditions build on those indicator values. They combine these numbers to determine if a trade should be initiated.
Precisely. Different conditions are needed for entry and exit signals, but the core function is using the indicators to give a yes or no answer about the ideal time to enter or exit a trade.
So, signal is just a set of those conditions for different trade signals?
Yes, effectively. They use indicators to formulate the rules and give clear, binary output for trade decisions. The critical distinction is the different rules for buy and sell signals.
Okay, so strategies combine entry and exit signals. But how does the system determine the trade size?
Trade size is part of the strategy. It involves money management. Simple methods use a percentage of remaining capital. More complex strategies analyze historical data and performance metrics.
Risk management is crucial. What safeguards are built into the strategy?
Absolutely. Risk management involves protection against price drops. This could be stop-loss orders, take-profit orders, trailing stops, or even limits on open positions. Methods vary, but the goal is consistent.
So, the strategy encapsulates the signal, size, and risk management components. Does it also involve parameters like indicator settings?
Exactly. Indicator values, calculation time frame, and other parameters are vital parts of a strategy. Different theories and approaches need different parameters.
This makes sense. Can you elaborate on the role of theory in this process?
Theories provide the underlying logic for signals, but not the specific parameter values. The theory outlines the conditional logic, while the strategy adds the parameters to translate it into an actual trading system.
So, a strategy essentially combines signals for entry and exit, capital management, and risk control. But how does it incorporate the specific settings of indicators like Bollinger Bands?
Right, the strategy needs the values of those indicator parameters. For example, the number of standard deviations for Bollinger Bands, or which candles are considered in a condition, all become integral components of the actual strategy, rather than being general theory.
And the theory defines the general logic, but not the specific indicator values?
Precisely. A theory outlines the conditions for signals. It might say enter when the closing price crosses above a moving average. But the specific moving average, time frame, and other parameters are elements of the strategy itself.
So, how do you, as a trader, manually develop a strategy based on a theory?
I start with a theory. It's an idea for a strategy. Then I test different combinations of indicator parameters, time frames, and capital management methods on historical data to see if it works.
That process of testing involves experimenting with different values for indicators?
Yes, it does. The specific numbers for indicators parameters, the time frame for the indicators, and how many previous candles to consider are all explored and tweaked to create a robust and profitable setup.
Okay, so a theory outlines the logic of the signals, but not the specifics of the indicators.
Exactly. It's the general idea, like cross above the moving average, but not which moving average or time frame. The strategy fills in those details.
How does a theory get tested for viability?
The system applies some algorithm to assess the potential profitability of the theory. It's not just a subjective evaluation.
And if a theory is deemed workable, what's the next step?
The system searches for the best strategy based on that theory. It involves finding optimal combinations of indicator parameters.
So, the system's search process hinges on identifying profitable strategies. But how does it determine profitability?
By testing various strategies based on that theory on historical data. This checks how well the strategies perform.
Okay, so the system generates theories either manually or with a generator. But how does the theory generation process work, specifically?
The generator needs signal templates as input. These signal templates essentially define the structure of how conditions are formed for signals. The generator takes these, fills them in with various indicator combinations, and creates new signals based on those templates.
And what about the specifics of building those signal templates?
Think of them as blueprints. A template might have slots for certain types of indicators and comparison operators, greater than, less than, etc. The generator then plugs in actual indicators like RSI, moving averages, etc., into those slots, creating unique signal configurations.
So, the templates themselves specify a particular logic.
Correct. The logic is predefined within the template. The generator simply varies the indicators, creating different signals based on the templates.
How would you ensure the generated signals are meaningful?
Templates are crucial. They act as guidelines, ensuring signals are coherent and have defined logical structures.
Okay, so signals are built using indicator comparisons and logical operators. How are these indicator values used in practice?
The signal's logic defines which indicators are used and how they are combined. For example, if indicator _1 is greater than indicator _2 and indicator _3 is less than indicator _4, then a bi-signal is generated.
The example shows a complex signal with multiple conditions. How are these complex conditions handled?
Conditions are grouped. The example uses and groups. For instance, to bi, multiple conditions must be true simultaneously, like LRC crossing WMA and RSI being below a threshold. Additional conditions, like BBW exceeding a value, further refine the signal.
The example also references previous candles. How does the system account for this?
Time frames and candle intervals are crucial parameters. The signal considers data from preceding candles in order to determine a particular signal, buy or sell. This is explicitly stated within each conditional check in the signals.
What about the presentation of a signal in the form of code?
The presented code formats signals in an organized manner, like signal to open and signal to close, with distinct logical operators. Each signal is a predefined logical operation, making it easier to implement in a programming language. This makes the signal reusable and testable.
So, the templates dictate the structure of the signal logic?
Correct. The example demonstrates the template, where the logic of the signal is defined before filling it with particular indicators. This structured approach ensures clarity and predictability in the signal generation process.
Okay, so signal template structure conditions. But how do these templates handle complex conditions like condition _1 and condition _2 or condition _3?
Templates define groups. A template might have placeholders for different logical operations, and/or. The generator uses these groups to create complex conditions. It substitutes indicators into those placeholders.
So, the grouping is part of the template design?
Precisely. The template defines the structure, including the grouping of conditions. The generator fills in the specifics.
Why use templates instead of a purely programmatic approach?
Templates offer structure and reduce the combinatorial explosion of possible signals. Using templates, you have a controlled way to define and generate complex conditions. A purely programmatic approach could lead to very complex, hard-to-understand code for generating signals.
What limitations do signal templates impose on the complexity of signals?
Templates, by their nature, limit the depth and scope of conditions. The template design ensures a consistent structure, making the generated signals more manageable. The trade-off is a potential loss in the sheer number of possible complex signals compared to a brute force programmatic approach.
What's the advantage of the brute force method, and when might it be useful?
Brute force is potentially more flexible, allowing arbitrary signal complexity. However, this is often impractical for the number of combinations. It's computationally expensive. But for simpler scenarios or specific niche conditions, brute force approaches might be adequate. But for scaling, a template method is better.
How does a user define a signal template?
A user creates templates specifying the structure of signals. Templates define the logical connections among conditions like an or and slots for indicators. It is a hierarchical structure.
Okay, so the user creates the templates and the generator instantiates those templates. How does that process affect the signal generation process?
It provides a structure and consistency. Users define logical frameworks, the generator inserts the actual indicators, leading to many specific signal combinations based on the same core logic defined in the template. This process ensures manageable and understandable signal generation.
Okay, so we've established how signals are generated. Now, what about capital management and risk control methods?
Right. These are predefined lists, not something we need to invent. The user simply selects from a list of available methods when setting up the theory generator. This is straightforward, and the generator applies each method to the generated theories.
The user defines theories, but the system's primary function is finding profitable strategies, not just generating theories. How does the process of finding profitable strategies begin?
The process hinges on a search method and a completion criterion. Given a theory, we need a way to explore potential profitable strategies based on that theory's rules.
What parameters need to be adjusted for a strategy based on a given theory?
The distinguishing factors are indicator parameters and conditional parameters, like the depth of candle analysis and time intervals. You adjust these aspects to vary possible strategies.
These parameters have boundaries, right?
Precisely. There are limits to candle depth, e.g., 0 to 50, and specific time intervals, 1 minute, 2 minutes, etc. These factors are vital constraints for the exploration process.
So, we're looking at the loopback period, time interval, and candles deep parameters. How do these limitations affect the strategy generation process?
These limitations drastically reduce the number of possible strategy variations. The loopback period, for example, limits how far back the indicator looks. This makes the search space manageable, although still considerable. The finite time intervals restrict the analysis.
Okay, I understand how these limitations affect possible values. How do we calculate the total possible strategy variations given these limits?
You calculate the total variations by multiplying the number of possible values for each parameter. For our first indicator, with loopback periods ranging from 2 to 300 with a step of 1, that is 299 possibilities. There are 12 time interval values, and candles deep has only one value. The calculation illustrates a significant reduction compared to a brute force approach.
The calculation shows a reduction in the number of variations, but that calculation was incorrect. How is the correct calculation made?
Correct calculation is 299 loopback period possibilities, 12 time interval possibilities, 1 candles deep possibilities equals 3,588. So there are 3,588 strategy variations for this one parameter combination.
That makes sense. We've limited the possible values, but the total number of possible strategies is still a considerable number if we consider multiple indicators and conditions. How can we make sure we can handle such a large number of calculations efficiently?
We can't simply check every possibility. This is why optimization algorithms are crucial. They allow us to strategically explore the space of possibilities without checking every combination.
Okay, we've calculated variations for one indicator. Now, we need to consider the rest of the signal indicators. How many potential variations exist when combining all the indicators in the signal?
The total possible strategy variations result from multiplying the individual variations for each indicator and condition. Each combination represents a unique strategy. The number gets very large very quickly.
Right. The calculation implies a massive number of potential strategies. How does this impact our search strategy?
The sheer volume of possibilities necessitates using optimization algorithms to avoid a brute force approach. These algorithms strategically explore the parameter space, finding potentially successful solutions without testing every single option.
What criteria help optimize our choices?
The optimization criteria for profitable strategies aren't simply random calculations. We need to define a function, the objective function, to measure profitability. For example, we could use average monthly profitability. The optimal strategy maximizes this function.
What are the important factors in defining the objective function?
The objective function needs to capture factors like profit, win rate, maximum drawdown, and recovery factors. A well-defined function helps us find strategies that perform well over time, rather than those with fleeting gains or periods of extreme loss.
By focusing on more than just profitability, we can ensure the strategies are more reliable for long-term success. Considering the vastness of this problem, what are the practical implications for developing our system?
This means we need a system capable of efficiently applying the optimization algorithm. We will need tools for calculating performance criteria and a robust framework for managing large sets of data, as well as a way to filter the vast amount of results to find only the best ones that meet predefined criteria.
Wow! That calculation for potential strategy variations is astronomical. It's clearly impossible to test every single one. What practical steps can we take to address this immense number?
Precisely. We need to leverage optimization algorithms. These algorithms intelligently explore the parameter space, searching for promising strategies without exhausting all possibilities. They look for local optima, which might not be the absolute best but are often good enough.
Right. So, we're not just randomly testing every combination. How do these optimization algorithms work in our specific context?
Optimization algorithms try to find the best set of parameters within the defined bounds for each indicator. They consider factors like historical data and the objective function. The process iterates, refining the search based on previous results.
That sounds promising. But how do we define the limitations for the search in terms of time and resources in an effective way?
We need to define constraints. How long is the search process acceptable? How many iterations should each algorithm take? Are there limits on the number of strategies that we aim to calculate in one optimization run? Establishing these practical limits is important.
So, we need both an optimization algorithm and clear criteria for stopping the optimization process to prevent running indefinitely. What else do we need to factor in when designing the system to efficiently explore such a vast search space?
To efficiently use optimization algorithms, we need a system for storing and managing the results of those calculations to keep track of progress. We need an effective method for evaluating the fitness of a particular strategy, and a robust framework to handle potentially large amounts of data and results.
Okay, so optimization algorithms aim to find the best parameter values for our strategies. How do we define the best in this context?
The best is represented by the objective function, which measures a strategy's profitability. A good example is average monthly profitability, calculated as ending balance, starting balance, / starting balance.
And what are the critical components of this objective function? It can't just be raw profit, right?
Precisely. We need to incorporate factors beyond pure profit, such as the win rate, maximum drawdown, largest percentage loss, and recovery factor. A comprehensive objective function considers these to identify robust, sustainable strategies.
Understanding the function's importance is key to the algorithm's success. How do we ensure the algorithm explores the full range of potential parameter values, given the vastness of the search space?
We need constraints. The algorithm should be restricted to a specific range of values for each parameter. This ensures we don't waste time on irrelevant or infeasible scenarios.
What practical limits are important for the algorithm? How long should it search, for instance?
We need to set a maximum number of iterations, ensuring the search process doesn't run indefinitely. We also need a threshold for determining acceptable results. How close does the algorithm need to get to identify a good strategy?
If we constrain the search space and set limits for the algorithm, what's the impact on the algorithm's accuracy and coverage?
Constraining the space means the algorithm won't find the absolute best strategy, but it will find potentially profitable ones in a reasonable amount of time. Balance between coverage and accuracy is critical.
So, this optimization loop sounds iterative. How do we choose the initial parameter ranges?
We start with a broad range for each parameter, like loopback period, then gradually narrow it down. This initial broad range allows the algorithm to explore the entire parameter space.
But narrowing the ranges is crucial for efficiency. How do we determine when to narrow them?
We can use the results from the optimization runs. For example, if most of the best strategies found in one iteration fall within a certain range for loopback period, we can restrict that range for the next iteration.
What if some good strategies are outside the initially chosen ranges?
That's a risk. To mitigate this, we can implement a mechanism that occasionally expands the search space, ensuring that we don't inadvertently exclude potentially profitable strategies.
How do we balance thoroughness in exploring the parameter space with the need to avoid excessive computational time?
Balancing thoroughness and time is tricky. We use optimization algorithms which aim to find good solutions quickly, not necessarily the absolute best. The initial broad search is crucial, and a stopping criteria for the search iterations is essential.
And what about the stopping criteria? Is it just the number of iterations, or is there something more sophisticated?
The stopping criterion could be a combination of factors: a fixed number of iterations, or a threshold for how much the optimal value is changing between iterations. We want the process to stop when it's unlikely that further iterations will dramatically improve the results.
So, using a breadth-first approach initially with larger parameter steps is a way to quickly eliminate bad theories. But how do we identify these truly bad theories?
We need a quality condition. This involves evaluating generated strategies based on factors like the number of trades, the win rate, maximum drawdown, and average monthly performance. Strategies that don't meet certain criteria, for instance, a minimum number of trades or a certain win percentage, get discarded.
How do we set the parameters for this quality condition? Is there a universally accepted standard?
No single standard exists. The criteria need to be tailored to the specific trading context and the type of strategies we're trying to find. It's about setting realistic yet achievable expectations for robustness and profitability.
And what happens to theories that pass the initial quality check? Do we just proceed with optimization?
No. A theory that passes the quality filter is further explored by iteratively refining the parameter ranges. That's where a more targeted, depth-based approach with smaller steps and refined ranges comes in.
Why not just use a depth-first approach from the start? It seems more targeted.
A purely depth-first approach can get stuck in local optima. The breadth-first filtering step is crucial for quickly discarding theories that have a demonstrably low chance of success, saving time on optimizing ones with little potential.
So, this quality condition filters theories. How do we decide on the threshold values for these filters, like the minimum number of trades?
It's very subjective, really. We need to consider the desired stability of the strategy. For instance, a higher minimum trade count might result in more stable strategies, but potentially fewer options overall. It's a balancing act.
Can we adjust these filters based on the type of instrument or market conditions?
Absolutely. Different assets might require different thresholds. A volatile market might warrant a higher minimum trade count for stability. A high-volume market might accept a lower win percentage. Flexibility is key.
What if a theory initially passes the quality filter, but then later, after more refinement during optimization, it falls short?
We need to track changes. A mechanism to reevaluate theories after adjustments to their parameters based on the quality condition, ensuring theories remain relevant.
What if a strategy that looks extremely good in simulations, but is based on a theory initially filtered out because it doesn't meet the basic quality criteria, is still viable?
That's a good point. A system should account for that possibility. The initial filter is designed to eliminate theories extremely likely to fail, yet there might be exceptions. We must account for this.
Okay, so if a strategy looks promising but doesn't meet initial quality thresholds, we shouldn't exclude it completely?
Exactly. The initial filter is a way to speed things up. We want to quickly identify theories with low potential, but not rule out potentially good strategies prematurely.
So, we need a way to reevaluate a theory even after the initial quality check?
Yes, a mechanism to revisit theories based on changes in parameters, a way to reevaluate based on the quality condition. This way, potentially promising theories not initially selected can still be considered.
How does this revised theory fit in with the idea of subtheories?
Subtheories represent different optimization approaches to the same theory. We can have multiple subtheories with varying optimization rules exploring alternative avenues based on parameters. So, a subtheory might be tailored for a theory that initially didn't make the initial quality cut but now has promising characteristics.
Does creating a subtheory require new settings, or is it inherent to the theory?
The subtheory is built on a theory but incorporates specific settings for optimization, including step sizes and parameter ranges. It's not a simple rerun of the original theory. It represents a specific exploration based on the theory.
What about the trade-offs between speed and accuracy in creating subtheories?
A balance is needed. Initial subtheories might use broader parameter ranges, optimizing for speed. Subsequent subtheories refine these parameters, aiming for higher accuracy. The initial broad steps are helpful for exploring a wide space quickly.
So, initial subtheories use wider parameter ranges for speed. Then we refine those ranges in later subtheories for greater accuracy?
Exactly. It's a trade-off. We explore a broader search space initially, and then narrow in on more promising areas as we get more data. It's like using a wide net first, then a finer one.
How do we determine the best step size to use in each subtheory?
That's a critical point. We could use the results from the previous subtheory to inform the parameters for the next one. For example, if a particular parameter range consistently yields successful strategies, we'd narrow in on that range in the next subtheory.
What if a parameter doesn't have a clear optimal range in the results of the initial subtheory?
Then we probably need to adjust our strategy. It suggests a deeper look into the parameter's impact. We might explore additional subtheories with different variations of this parameter step.
If we iteratively reduce the step, might we reach a point where we are effectively doing a brute force search again?
Yes, that's a possibility. We need to set a stopping criterion. For example, we might specify a minimum step size. Once we hit that, we can switch to brute force. It also depends on the total number of strategies in the subtheory and how many are considered to be high quality or suitable.
Okay, so we're taking the best 5 strategies from the initial subtheory to refine our loopback period range. How do we ensure that these strategies are truly representative?
Good point. We should consider using a more sophisticated selection method than just taking the top 5. Maybe a weighted average based on profitability, stability, and other factors. That helps prevent biases from affecting the next subtheory search range.
Is there a risk of narrowing in on a local maximum too quickly?
Potentially. We need a strategy for exploring different subranges within the parameter space, not just focusing on the top strategies. For example, exploring a few subranges around the best loopback period values might give us a better understanding of the optimal space.
How do we choose the number of subranges to explore? And how do we balance exploration versus exploitation?
A good approach is to specify a percentage or fixed number of subranges to explore. This helps ensure we cover the broader potential search space without spending too much time on areas where performance isn't likely to improve significantly.
With a smaller step size in each subtheory, won't the number of strategies increase dramatically, potentially defeating the purpose of efficiency?
Precisely, and this is a vital point. We need a quality condition to manage the number of strategies. By specifying a threshold on profitability, stability, or other metrics, we filter out strategies that aren't worth exploring further. This keeps our approach efficient.
Can this quality condition be applied at each step of the subtheory iterations?
Yes, the quality condition should apply at each stage of the iterative refinement. It filters potentially promising strategies before moving on to the next subtheory. ensuring that each iteration is focused and efficient.
So, we refine the parameter ranges iteratively, but how do we prevent getting stuck in local optima?
Good question. Exploring multiple subintervals around promising areas can help. Also, adjusting the step size based on the iteration number or the total number of strategies is a technique to balance exploration and exploitation.
How do we ensure the selected strategies in each iteration are truly representative?
We need to refine our selection criteria. A weighted average based on profitability, stability, and other factors could be better than simply taking the top strategies.
What about the trade-off between exploration and exploitation? How do we manage the exploration time?
Specifying a percentage or fixed number of subranges to explore is a reasonable approach. That way, we ensure coverage of the wider parameter space without excessive time spent on less promising areas.
How do we determine the exit criteria for this iterative process?
Using a double condition is a good idea. The first condition is the number of iterations. The second condition is the number of high-quality strategies found, in which case a brute force approach could be used.
What's the process for selecting strategies for forward testing?
We sort the strategies by the optimization criterion and select the ones that satisfy predefined quality criteria. This process continues until we either collect a sufficient number of strategies or exhaust the pool of potential strategies defined by the selection criteria.
What is the importance of forward testing with new instruments?
Crucially, forward testing on unincluded instruments ensures that the strategies are generalizable and not overfitting to specific instruments. It reveals how strategies would perform in a new market environment.
How can we implement the forward testing and handle the quality criteria involved?
The system should follow a predefined list of strategies sorted by the optimization criteria and apply quality criteria. This continues until either the desired number of strategies is collected or the pool of eligible strategies is exhausted.
Okay, so we got forward testing. How do we define the new instruments for this testing?
Good point. We should use instruments not included in the initial search. This ensures we're testing the strategy's adaptability to different markets. We need a separate dataset.
How do we handle potential performance differences between these new instruments and those used in the initial search?
We need a clear way to categorize instruments, perhaps by asset class or similar market characteristics. This helps compare strategies across different types of instruments, rather than just a simple yes or no pass/fail.
What about real-time monitoring? How do we identify when a market instrument changes type?
That's a key aspect. We should use market data feeds to track changes in price movements and trading volume for each instrument. We'll need indicators and thresholds to define the type transitions.
How do we balance the accuracy of identifying a market instrument's type and avoiding frequent unnecessary strategy on-off toggles?
Precisely. We should set a threshold for change in price or volume, as well as time durations. This prevents the system from constantly reacting to small fluctuations and reduces unnecessary strategy adjustments.
What safeguards are needed to prevent the system from losing large sums of capital during real trading?
Robust risk management is essential. We need a dedicated risk control module within the real-time monitoring system to continuously assess the performance of each strategy and trigger appropriate actions, such as closing positions, if necessary.
Okay, so search settings need to be integrated into the theory itself. How do we ensure consistency across different theories?
We need a standardized format for search settings. This way, all theories use the same parameters and ensure a consistent search process, regardless of how they were created.
How do we handle the various segments of historical data for different strategies? Managing those data sources correctly is key.
Right. A robust data management system is crucial. We need to store historical data for different instruments and periods, and ensure easy retrieval based on the user's specified theory.
What about error handling and edge cases in the data management system?
We need checks for data validity, completeness, and inconsistencies. This prevents errors from affecting the strategy searching and forward testing process. Robust error handling is important.
How do we handle multiple exchanges? Integration with various exchanges is essential.
We need an intermediary layer or API gateway to handle communication with different exchanges. This ensures the system can access data from multiple platforms without requiring direct exchange-specific code for each.
What safeguards are in place if an exchange is temporarily unavailable?
The system needs to handle temporary exchange outages gracefully. This might involve queuing requests or using cache data when possible. Back-off mechanisms should be included.
How do we categorize instruments into types, and how frequently should we update these types?
We should define clear criteria for instrument types based on market characteristics. We'll need a mechanism to automatically update these types based on price and volume movements. A defined time frame for these updates is necessary.
Okay, so search settings are part of the theory. How do we ensure these settings are validated before running the search process?
Good point. We need validation rules for the search settings. This prevents invalid or poorly defined searches. We should check for things like parameter ranges, instrument lists, and other critical values.
How do we handle updates to the theory after the initial search begins? Can we adjust settings mid-process?
Adjustments should be allowed, but with careful consideration. Changes to the theory may necessitate a fresh search, or perhaps only adjustments to specific parameters. We'd need to develop a system for updating the search in progress.
How is the selection of historical data handled by the system? Different theories may need different time frames and data sets.
The system needs a dynamic data selection process. The user should specify the required time frame and instrument data. The system handles the retrieval and preparation of this data based on the theory.
What error handling is put in place if there's a problem retrieving historical data for a given instrument or time frame?
We need robust error handling in data retrieval. The system should report any errors to the user, providing explanations for issues like data unavailability or incorrect formats. This is crucial to maintain reliability.
Okay, so iterative narrowing of parameters for strategy search. How do we define the initial parameter ranges?
Initial ranges need to be based on user input or default values, ensuring a broad search space to begin with.
How do we determine when to stop narrowing parameters? A fixed number of iterations seems insufficient.
A combination of maximum iterations and a threshold for parameter change is needed. If parameters no longer change significantly, we stop, even if the maximum iterations aren't reached.
How do we manage the trade-off between accuracy and computational resources? Narrowing too aggressively could be costly.
We need a way to dynamically adjust the narrowing step based on the results of each iteration. More aggressive narrowing happens if there's a strong signal in the results of the previous step.
What about strategies that don't perform well in the forward testing phase? Do we just discard them?
No, we should track the performance of strategies over time and use this information for optimization later. Discarding good strategies simply because they aren't immediately profitable is a mistake.
How do we define the quality criterion in the search settings? Should it be profit only?
The quality criterion should be a combination of factors, including profit, drawdown, stability, and other relevant metrics. The user should have control over the weighting of these factors.
How does real-time instrument type monitoring work? How do we detect changes?
We need a real-time data feed from exchanges. This feed should track price and volume changes. A machine learning model might be useful in classifying types of instruments based on these changes.
How do we handle the complexity of managing strategies across multiple instruments?
A system that manages strategies and instruments independently will solve this. A central control module, overseeing all instrument and strategy interactions, is necessary.
How do we define a tool type, and what safeguards are in place to prevent frequent type changes?
Tool types should be based on observable characteristics like price movements, volatility, and volume. We should incorporate a buffer period to avoid excessive strategy adjustments due to minor fluctuations.
How does the external audit of strategy performance work? What constitutes discrepancy?
The external audit should track key metrics like balance, profit/loss ratios, and trade frequency. Discrepancies could be a sudden drop in balance, unusually high or low profits, or unusual trade patterns.
How do we handle planned system updates without impacting live trades?
We need a system for planned maintenance. This includes pausing or suspending strategies during updates and resuming operations after the update is complete. Error handling is crucial.
What are the backup plans for unexpected issues like exchange shutdowns or outages?
We need failover mechanisms to prevent data loss and ensure continued trading. The system needs to have strategies to automatically disconnect from the exchange in case of outages and reconnect when the exchange resumes operations.
How do we architect this large-scale program for dozens of exchanges and instruments?
Modular design is key. Separate modules for each exchange interaction, instrument monitoring, and strategy execution will enhance the system's flexibility and scalability. Robust testing is essential across multiple exchanges.
What about security considerations?
We need robust security measures to protect against unauthorized access to funds or to the system itself. The security protocols should be integrated into each module to handle data encryption and access control.
Okay, so position lifecycle. How do we represent the different states a position can be in?
We need to define various states like open, partially filled, canceled, and rejected. Each state needs clear definitions and transitions between them.
How do we handle discrepancies between the system's internal order and the broker's confirmation?
We need a mechanism to track discrepancies. This might involve logging events, comparing internal order statuses with broker confirmations, and handling timeouts.
What about the timing aspects? Broker confirmations might be delayed. How do we handle potential conflicts?
Timeouts are crucial. A timer on system orders is necessary to detect potential delays in broker responses. If confirmation isn't received within a certain time, we handle the situation with a fallback plan, such as automatically canceling.
If an order is partially filled, how do we manage the remaining portion?
A system order should maintain the remaining quantity. The system needs to reevaluate the situation and create another order to meet the initial request.
How do we prevent cascading failures if a broker rejects a system order?
We need to retry the order in a configurable time frame. However, repeated failures for the same order should trigger an alert. A mechanism to flag potentially problematic brokers is necessary.
What about error handling for various potential broker errors?
We need to categorize broker errors to understand why it happened and set up appropriate retries and reporting. The goal is to make the order workflow robust enough to handle unexpected broker issues.
Okay, so we've got this position opening process. How does the system handle a partially filled order?
The system needs to track the remaining quantity of the order. It should then automatically place a new order to fulfill the original quantity, adjusting as needed.
What if the initial market order gets rejected? How many retries should we allow?
A configurable retry mechanism is needed. We should set a limit for retries, say 3 times, with increasing delays between attempts. Beyond that, an alert is triggered to investigate the rejected order. We need to investigate broker-specific reasons for rejection, like insufficient liquidity.
What about the order status updates? They're asynchronous, right? How will we handle delays in broker confirmation?
We need a system to handle asynchronous order status updates. Timers are needed with timeouts in place. After a timeout, the system can assume the order failed and take action, e.g., cancel, retry, alert.
How do we ensure that the system doesn't create too many outstanding orders for one position?
Order processing should be sequential. The system should only create new orders after the previous order has been confirmed or failed. This prevents a buildup of orders for a single position.
If a broker returns an error, how do we gracefully handle that without impacting the rest of the system?
Error handling needs to be robust with a separate error queue or processing mechanism. Errors from one broker shouldn't affect orders with other brokers. Appropriate logging is essential to understand and track the failure points.
Okay, so capital management. How does the fixed interest method work exactly?
The fixed interest method takes a percentage of the current balance as the maximum purchase amount for an asset. It's straightforward, easy to implement.
How often does the system check for balance changes and recalculate the maximum purchase amount?
It should check after every price change for the asset, or perhaps at regular intervals. The frequency would depend on how volatile the market is.
If the price of the asset fluctuates rapidly, how does the system deal with these frequent calculations?
Efficient calculation is essential. Using a caching mechanism for recent balance and price data could help with speed. A queue for purchase calculations might also improve responsiveness.
What if a strategy indicates a need to buy more than the calculated maximum?
The system shouldn't allow the purchase. The capital management module will prevent exceeding the calculated maximum purchase amount based on the fixed interest rate.
How do we handle situations where the fixed interest percentage needs adjustment?
The percentage should be configurable, allowing the user to adjust the rate in the system settings, potentially through a configuration interface.
How does the system prevent the purchase amount from becoming unreasonably small or large?
Setting reasonable bounds on the percentage would be essential. A user-defined minimum and maximum percentage limit on the purchase amount would help prevent extreme values. A mechanism for user input would be needed.
What are the potential limitations of the fixed interest method?
Fixed interest lacks sophistication. More complex methods like dynamic allocation or risk-based approaches might be necessary for more advanced trading strategies. The system should be built to facilitate adding more complex methods.
Okay, so take profit and stop-loss orders. They don't execute immediately. How is the trigger price calculated?
The trigger price is based on a percentage difference from the average purchase price. If the closing price crosses that threshold, the system order is placed.
How is the average purchase price determined? And what if it changes after the initial calculation?
It's the average price from all trades in the initial order. If the order is ongoing, the average recalculates as more trades occur. This is a dynamic calculation. We need to handle the adjustments to the trigger price if the ongoing order is partially filled.
What about situations with multiple buy orders in a single position? Does the average price recalculate from the new, combined trades?
Yes, the average price recalculates for all trades in a position. It's important for stop-loss and take-profit triggers to use this updated average, ensuring accuracy.
What safeguards are in place to prevent incorrect calculation of trigger prices due to noisy market data?
We need filtering on order trades for data quality. A configurable time window or data smoothing could help. Potential outliers or errors in trade reporting need to be addressed.
How does the system handle the possibility of an order being canceled after a trigger price is calculated but before it's executed?
If an order is canceled, the trigger is invalidated and recalculated when the order status updates to a fill state or a canceled state. Appropriate logging captures this process for diagnostics.
Let's say the trigger price is set, but the asset price doesn't reach it. What happens after a certain amount of time?
The system needs a timeout mechanism. If the target price isn't met within a configurable time frame, the trigger is automatically removed, and the position might transition to a different risk management strategy.
Great. So, how are trailing system orders different from take profit and stop loss in terms of their trigger mechanisms?
Trailing stops dynamically adjust their trigger price based on the asset's movement. The trigger price continually increases as the price moves up to capture more profit from any uptrend.
So, stop-loss orders trigger a sell order when the price falls below a certain level. How is this different from a trailing stop?
Trailing stops adjust their trigger price as the asset price moves. A stop-loss order has a fixed trigger. The key difference is the dynamic adjustment.
How does the trailing stop dynamically adjust the trigger price?
The trigger price is tied to a trailing price, which represents the average purchase price, and adjusts as the asset price moves. If the asset price rises above a certain threshold, the trailing price is updated.
How is the threshold determined for updating the trailing price? Is it always the same percentage increase?
A user-defined percentage threshold, decision coefficient, determines when the trailing price updates. This helps manage risk by ensuring the trigger price isn't too aggressively adjusted.
What happens if the price falls below the stop-loss trigger?
The stop-loss order triggers a sell order immediately, closing the position. This is distinct from the trailing stop, which aims for profit capture by following the asset's upward movement.
If the asset price fluctuates after the trailing stop is triggered, but before the order is executed, is the trailing stop trigger updated?
Yes, the trigger price adjusts, following the price's movement. The trailing stop is responsive and tracks the live market conditions as the asset price changes. This dynamic adjustment is a core element of trailing stop orders.
How do you prevent the trailing price from becoming too volatile, say, from rapid market fluctuations?
A parameter controlling the rate of trailing price updates could help. This would prevent overreactive price adjustments, and a reasonable limit on the percentage difference of trailing price changes would be necessary.
Okay, so the trailing stop formula isn't just a fixed percentage change. It narrows the profit/loss band. How does this narrowing factor work?
The narrowing is controlled by border change coef. It's a percentage that shrinks the distance between the profit and stop borders with each trailing price adjustment. This helps to prevent excessive profit/loss fluctuations in the order.
How do you determine the initial border change coef value? Does it depend on anything?
Border change coef is a user-defined parameter, part of the strategy settings. It impacts how quickly the trailing stop band adjusts to the price movement. A smaller value means a slower, more conservative adjustment.
What if the border change coef value is too high?
A high value might cause the trailing stop to react too quickly, potentially missing out on opportunities or creating significant losses from rapid price fluctuations.
How frequently does the trailing stop recalculate its boundaries?
The trailing stop recalculates its boundaries whenever the current price crosses the decision line and the decision signal is positive. A parameter controls the frequency of checks, so it doesn't check constantly and adjust every tick.
What happens when the price moves back below the decision line? Does the trailing stop price adjust?
The trailing price doesn't adjust back when the price moves back below the decision line. It only adjusts on a positive signal and crossing of the decision line in the upward direction. This ensures the trailing stop only adjusts in the profitable direction.
How do you handle potential overshooting when the price jumps beyond the expected range before the order is triggered?
A limit is needed on the maximum change in the trailing price. Overshooting is mitigated by limiting the percentage change between trailing price adjustments. This prevents the system from overreacting to very large price jumps.
Okay, so if the signal is yes, the trailing price updates. What if the price jumps, like in the example, from 97 to 105?
The trailing price would indeed update to 105. This dynamic response is crucial for capturing further gains. The stop and profit borders adjust accordingly.
How is the adjustment to the borders calculated with the updated trailing price?
The formulas for profit and stop borders use the new trailing price and border change coef. This adjusts the boundaries to follow the upward trend.
Does this mean the trailing stop will adjust even if the price momentarily dips below the decision line?
No, the trailing price only updates when the price crosses the decision line and the decision signal is positive. The trailing stop is designed to track price increases, not to react to short-term dips.
What if the decision signal is no?
If the decision signal is no, the trailing price remains unchanged. The stop and profit borders aren't updated. The system waits for another upward price movement across the decision line with a positive signal to adjust.
How does this example account for potential overshooting?
The system limits the percentage change allowed in the trailing price. It prevents excessively rapid adjustments from sudden market spikes. This maintains stability.
What happens if the price moves rapidly up, then rapidly down, before the order is executed?
The trailing stop would adjust the stop and profit borders according to the highest point reached since the last decision signal. The price would have to cross the decision line in an upward direction, and the trailing price would then be adjusted to the new higher price. The new trailing price would then form the basis for the new stop and profit calculations.
Okay, so the price dipped below the decision line. Why doesn't the trailing price adjust?
The trailing price adjusts only when the price moves above the decision line and the decision signal is positive. The system tracks upward movements, not short-term dips.
If the price jumps to 105, how does the trailing stop calculate the new borders?
The new trailing price becomes 105. The stop and profit borders recalculate using this new value and the border change coef. This ensures the trailing stop continues to adapt to upward price trends.
Does the fact that the price dipped to 95 affect the calculation for 105?
No. The calculation for 105 only considers the trailing price's adjustment to 105. The dip to 95 doesn't affect the calculation for the new upward movement.
Does the decision count variable change when the price dips below the decision line?
No. Decision count only increments when the price crosses the decision line and the decision signal is positive.
Are there any limits on how much the trailing price can change in one recalculation?
Yes, the system limits the percentage change allowed between trailing price adjustments. This prevents overly rapid responses to price volatility.
So, the price hits 105, triggering a position closure. How does the system handle cases where the price moves rapidly up and then down before execution?
The system considers the highest price reached since the last decision signal. This ensures the trailing stop adjusts to the peak, not just the immediate price. The stop and profit borders adjust using this peak as the new trailing price.
Are there specific mechanisms for defining the decision signal?
The decision signal is a custom function. Could assess market sentiment, volume, or other factors, not just price. The user configures the logic of this function in the strategy.
This process of scaling indicators is crucial. How is the scaling updated as new data arrives?
The scaling recalculates with each new segment of historical data. New minimum and maximum values for each indicator are incorporated into the scaling.
How does this ensure reliable comparisons across different indicators?
The scaling ensures all indicator values are expressed on a 0 to 100% scale. This allows for accurate comparisons between different indicators, regardless of their initial ranges.
What are the potential pitfalls of using this scaling method?
Potential pitfall could be the sensitivity to the chosen data window. Too small a window might produce noisy scaling, and too large a window might not reflect recent market movements. Proper historical data window length is critical.
How is the length of the historical data window determined in practice?
The length is a user-defined parameter, part of the search settings. It's important to strike a balance between responsiveness to recent market trends and avoiding noise.
Okay, so the maximum indicator value is 20, and the minimum is 9. How is the value 18.18 calculated for October 2nd, 2018, 8:05?
Using the formula 11 to 9 / 20 to 9, 100, where 11 is the current value, 9 is the minimum, and 20 is the maximum for that period. This scales the value to a 0 to 100% range.
What happens if the next data point for that indicator is 22?
The minimum and maximum values will be recalculated for the new segment of historical data. The scaling will adjust using the new minimum and maximum values. So, the scaling would change based on the updated data window.
Does the scaling process introduce any potential bias?
Yes, the choice of historical data window introduces a bias. A very short window can be noisy, while a very long one might not reflect current market conditions. Selecting an appropriate window is crucial to prevent bias.
How does the system determine the appropriate historical data window?
The user defines the length. It's a balance between capturing recent trends and preventing noise.
Are there different ways to choose the window length?
Yes. You could use methods like moving averages, exponentially weighted moving averages, or a fixed user-specified window length. Each method has trade-offs in capturing recent trends and avoiding noise.
Looking at the scaled values, how is the system handling the jump from 0 to 100 and back down?
The scaling adjusts dynamically with each new data point. The min and max are recalculated for the current data segment. This accounts for peaks and valleys in the data.
How does the system ensure the scaling doesn't create artificial patterns or inconsistencies?
The choice of the data window is crucial. A balance is needed between reacting to recent data and avoiding volatility. The correct window prevents artificial patterns.
How can the system be improved to handle different types of indicators with varying ranges?
The scaling formula remains the same, but the system could employ different data window lengths based on the type of indicator. This would address different response times for various market fluctuations.
Is there a way to adjust the scaling based on the volatility of the instrument?
Yes, adjusting the data window length in response to volatility can improve scaling accuracy. A higher volatility instrument might require a shorter data window to respond to fast price changes effectively.
How does the system manage situations where the maximum value is very close to the minimum value for an indicator?
The scaling formula still works, though the resulting scaled value might be very high or very low. It's more critical to use the correct data window length in those cases.
Okay, so we're talking about the theory generator now. How does it choose which signal templates to use?
The user selects the templates, and the generator applies them. Different combinations of indicators are substituted into the templates to create new signals.
How does the system handle the potential for infinitely many combinations of conditions and groupings?
Signal templates limit the possible combinations. These templates provide the structure for conditions, and the generator populates them with indicators.
What about the capital and risk management methods? How are they incorporated?
The user specifies a list of methods for the generator. The generator then creates theories incorporating these methods.
This process seems computationally intensive. How do we limit the combinations effectively?
The generator uses the signal templates to narrow down the possibilities. The defined template parameters ensure a manageable quantity of combinations.
How do we verify the efficiency of these generated theories?
We need a process to evaluate each theory's potential. A key step will be evaluating the theory's performance using historical data. This step is crucial for eliminating theories that won't work.
What criteria are used to assess the viability of theories?
The criteria for viability are defined by the user. It could be profitability, stability, or other relevant metrics. A good theory generator will handle this by including metrics to assess theories.
Can you give me an example of a theory evaluation metric?
An example metric could be the percentage of profitable trades over a specified historical period. Another metric could be the maximum drawdown experienced by the strategy during that time. A combination is typically used.
How does the system handle situations where the generated strategies perform poorly in forward testing?
The system flags unsuitable strategies based on the forward testing results and predefined criteria. It adjusts the search parameters accordingly to find better options.
What are the specific criteria for evaluating strategies during forward testing?
The criteria are defined by the user. They might include profitability, stability, and maximum drawdown.
How does the system prevent overfitting to the historical data used for forward testing?
Using different sets of historical data, the system tests strategies on unseen data. This helps avoid overfitting to specific patterns.
How can the system handle new instruments?
The system categorizes instruments based on characteristics. Strategies are evaluated based on their performance on instruments of the same type.
How does the system decide what constitutes a type of instrument?
Users define instrument types based on characteristics, like market capitalization, sector, or trading patterns.
How does the system dynamically update the instrument types during real trading?
The system observes real-time data to adjust instrument classifications. If an instrument's characteristics change significantly, its type is updated.
How is the system ensuring its response time in such dynamic updates?
Fast, real-time data processing is crucial. Efficient algorithms and optimized data structures are needed for timely instrument type updates.
How is a strategy disconnected from an instrument after an update?
The system manages the disconnection process and ensures any open positions are closed before the strategy is disconnected. Efficient processes are needed to avoid conflicts or losses.
How is the system's real-time trading operation monitored?
An external monitoring system checks strategy performance and balance. If anything is out of the ordinary, the system halts the strategy.
What is the mechanism for handling potential issues like exchange outages or system updates?
The system has predetermined procedures for handling such disruptions. These procedures will stop or pause the impacted trading operations during any downtime.
How is the system's design for a large-scale operation ensuring overall robustness?
Scalable and modular designs are needed to accommodate multiple exchanges, instruments, and strategies. This allows the system to expand and adapt to diverse conditions.
Okay, so we're diving into the life cycle of a position. What exactly is a position in this context?
A position is distinct from an internal system order and a broker order. It's the entity initiating system orders. One position can trigger multiple system orders.
How are different order types, like stop loss and take profit, handled within the system?
The system creates corresponding system orders for these types, but not all will immediately result in broker orders. It depends on the broker's order type support and market conditions.
What are the various statuses an order can have within the system?
Orders can be new, partially filled, canceled, or rejected. Processing these statuses correctly is crucial.
How does the system handle asynchronous order updates from the broker?
A position processing mechanism within the platform correctly handles delays in receiving order updates from the broker. This ensures accuracy in position management.
Now about capital management. How does this interact with the position life cycle?
Capital management methods receive strategy data to determine the maximum purchase amount and the strategy for additional assets.
What's an example of a simple capital management method?
A fixed interest method calculates the maximum purchase amount based on a percentage of the current balance. It doesn't account for repurchase strategies.
How does risk control, specifically stop loss and take profit, work within this framework?
Stop loss and take profit orders are system orders, not immediate broker orders. They are triggered when specified price thresholds are crossed.
Can you illustrate how the average price of transactions influences stop loss and take profit order placement?
The average price of transactions is used to calculate the trigger price for stop loss and take profit orders.
How is a trailing order different in its triggering mechanism?
Trailing orders dynamically adjust their trigger prices based on the trailing price. This trailing price changes depending on the market action.
How does the formula used for trailing orders prevent the strategy from becoming overly aggressive?
The formula includes a factor to narrow the acceptable price range between profit and stop. It ensures the trailing price adjustments are not excessive.
What are the variables necessary for a trailing order to function correctly?
Trailing price, profit border coefficient, stop border coefficient, border change coefficient, decision signal, and decision count.
What happens if the price crosses the profit border?
The position is closed.
How does the system address the issue of different scales among indicators?
The system scales indicators to a common 0 to 100% range for accurate comparisons in conditions. This scaling is dynamic, adjusting as new data arrives.